everybody, my guest today is Sam Aldar. Sam is a PhD. He's working at Dyson as a associate principal engineer, and uh, there's really two really exciting things about Sam. One is he does these amazing videos and renders of circuit board electronics, kind of like what you see in Altium in the 3D mode, but done with kind of the photorealism in a program called Blender. He's going to show us out today. And also, Sam was a really hardcore electrical engineer, so he's done some amazing work in wireless power. He goes into how that works, kind of the challenges there, how to do the simulations for extracting inductance, and the contributions he's made in power supply topology that can enable some of these high power, high frequency power transfers. In his case, among other things, to be able to charge drones without any physical connection between the power supply and the battery charging. So fantastic to talk with Sam today, and I hope you enjoy it. So Sam, right now you're you're let's see, associate principal engineer at Dyson. Is that right?
That's correct. Yeah. Yes.
And before that, you were in academia for a while and wrote some papers.
I did. Yes. I was in academia from 2014 up to 2019 at Imperial College in London, and I was a researcher. It was a good place to kind of to try experiment with new ideas, play with new concepts, free from deadlines and writing theses and all that kind of stuff. So it was a good time. Yeah.
Fantastic. And what kind of things did you focus on?
So in my research, it was mainly about we worked on um, technologies for wireless charging and wireless power transfer, mainly for applications in drones and robotics. We wanted to have a way to be able to charge these drones and robotics without having to have somebody actually plug them in. So we know that these applications at the moment they're almost fully autonomous. It's only when they need to be charged someone has to plug them in. So that was the main research: is can we create a technology that would allow us to charge these drones and robotics without any cables.
What is the primary challenge with all that?
Yeah. So the
Like,
primary challenge is it was mainly efficiency and performance. We all know that we have now wireless charging for our phones and other applications, but it's almost limited to about 15 to 20 watts or so. And that's because the efficiency is a bit low. So we wanted to go to much higher power levels, 100 watts, 200 watts. And so the challenge was, can we get the efficiency to be high enough and the performance to be good for these very high power levels? And so it was mainly about developing new circuit topologies and power electronics, basically, to allow us to get these very high efficiencies.
awesome. And what is the world of publishing papers like? Well, what kind of what do
Yeah.
you?
Publishing papers, it's not easy. It's always the first paper is always difficult to get in. Um, Sometimes it depends on the journal, on which journal you want to publish in. So some are easier than others. Some are almost impossible to get in. But mainly for electronics and electrical engineers, especially in power electronics, the main journals you want to publish in are IEEE transactions on power electronics. That's the top one, or that's where all my papers have been published in. But it's mainly getting a good paper in. You have to have good description, good results. Not too much on equations and math. Generally, the reviewers tend to, well, nobody has time to read these kind of equations, but as long as you have good results and something new rather than incremental, then you have a good chance at publishing a paper.
Did it take you a few tries to get that first one in there, and
It
then you developed
did.
a reputation, that kind of thing?
I did my PhD starting in 2010, and And back then, my first paper almost got rejected 3 or 4 times, and each time then you take on the comments from the reviewers, and then you you improve your work, and then eventually they can't say no, and then you get in. So it's always the first one. Once you understand how the system works, and what sort of things or topics the reviewers generally look at, and how they evaluate you on. Once you are aware of these things, then then it should be easier afterwards. Uh, it might be worth, before publishing a journal paper, it might be good to go to a conference first and publish a conference paper. Generally, conference papers are easier to review. They're short, straight to the point. So it's good to start with conference papers, I would say, and then after that you build on those conference papers, or you combine one or two into a big journal paper. Um, that would be my advice for that. Yeah.
And if you had to highlight one or two of the things that you contributed, I guess, to the scientific community, what would those be in those papers?
So as I mentioned, my research was about wireless power, and the approach that I took is going to very high frequencies for power electronics. So typically in your Qi wireless power on your charger, it works at 200 kilohertz. I was going into the megahertz region, and that because you generally get better coupling of energy, and you're able to transfer more energy over a larger distance. The challenge is then in the power electronics and the circuits. How do you which circuit topologies do you use the to work at these frequencies? So my main contribution was I've developed a few new circuit topologies and amplifiers that can actually work at very high efficiencies, above 90%, and are able to tolerate different variations in loading. Um, Especially if you want to transfer power over a large distance, generally your receiver tends to move around a little bit. So that reflects back on the transmitter, and then so the transmitter needs to sort of still operate within its limits and keep high efficiency as the load changes. And so many of my papers were about new circuit topologies, tuning methods, how to ensure that your amplifier is always tuned and at its maximum performance.
Is that tuning a one-time thing, or is it dynamic, like constantly happening?
So there's both. So my first paper that I published was because in amplifiers generally you would, if you want to tune an amplifier, or for low power amplifiers, you would use variable capacitors or varicaps, where you apply DC voltage to it, and that changes
Hmm.
the capacitance of these components. The challenge with those is that they're quite limited in power, so you really can't work at tens of watts. So in order to then, how do you tune your then how, so the uh, approach I took is I went back in time in history, and there was a component that was used called satchable reactor, also known as a magnetic amplifier, and that component was, I think, was used before transistors, or even before vacuum tubes. It's quite simple. It's basically a transformer with a primary and secondary, and you basically apply DC current into the primary side, and that sort of saturates the core of the transformer, and then changes the inductance of the secondary. So think of it as the equivalent of the variable capacitor, but it's a variable inductor, let's say, where you apply DC current. And so that allowed me to go at much higher power levels, and certainly in the tens of watts, I would say.
That's really cool. So it's kind of like having two windings on the same core,
Yes, yeah,
and then you can saturate with just a DC current that has no effect otherwise on the
absolutely.
signal. That's
Yeah,
really cool.
exactly. Yeah, it has its limitations. It is a big component, a bit bulky, and I wouldn't say it's very efficient. So although I solved one of the problems where I was able to tune my circuit and where I make it work over a wide load range, I had the problem of efficiency wasn't as high as I wanted to be with that satchable reactor. So it solved one problem out of two. Um, so, but it was certainly, I would say it's a good example of sometimes using an obsolete piece of tech repurposing it and using it to solve a new challenge.
That's awesome. So tell me about how you got it. I saw you posted on LinkedIn fairly frequently, and you have kind of a following going.
Yeah, yeah.
How did you first get into the PCB rendering?
PCB renders, yes. So it started back when I was doing my towards the end of my PhD, basically. One of the things in academia is that we need to write proposals to get funding. And so, and also we need to do presentations to other groups. And I realized that having too much text on a slide or in a document, it doesn't get you anywhere. People have no time to read. People like to look at pictures. So then I started to put more pictures and visuals, and I was just taking the CAD drawings that I had of my PCB and put it in there. And over time, that slowly evolved. I thought, okay, these images are too perfect, too ideal. It's certainly when you actually build your circuit or build your system, it doesn't look anywhere anything like what those CAD images are. And so I started to experiment to get some let's say in uh, perfections in the drawings to make it look a bit more real. So like adding a bit of cables in there, adding a bit of objects in the scene, then the bench, and then the probes that would come in. And then things got a bit out of hand where I started to add a bit more like dust and other kind of particles in the scene to make it look like a proper lab bench environment. And that's how I got into that. Eventually, now in my job, I'm actually now using these illustrations to actually present my work to my line manager or other key important people, and that really actually helps quite a bit to sell your idea or your concept. When other people they have just simple images and text in their slides and documents, it's a bit boring. But once you have a nice picture, you can really have lots of it inspires them to ask you different questions, and it allows you to talk about different topics and conversation. It just changes the entire situation. And that's how I got into it. And I started. I was using different software that was available at the time. I started with Inkscape. It was just 2D images. Then I slowly started to get into 3D, and that time I was using a software called SketchUp, which was, I believe, initially part of Google, but then it's now become a separate company. So I was using a SketchUp, and then I was also experimenting with Blender back in 2014. But Blender at that time was not the same as it is now. It was still early in its development. It was very complex, very difficult to learn, lots of menus. It is still a complex software, but it's now much better, I would say, and certainly much more capable. And so now I use Blender for pretty much everything from just concept and visualizations to quick drawings, even graphs. It's becoming, if you look at my desktop, I've pretty much got Blender open all the time, Altium on one side, um, and just working between the two of them.
So it seems like most people probably would be familiar with, in Altium, let's say,
Yeah,
hitting the three key and then you get the 3D view and you can rotate
exactly.
that
Yeah,
around. And
yeah,
every time you do that, you relearn how to rotate it,
yes,
trying
yeah,
different
yeah.
things.
Oh, yeah,
Uh,
yeah.
so is that also how you started out in terms of like, oh, I'll take a screenshot of that render and throw it in my document, and then
That definitely helped a lot, actually. I think that this is what really got me into, but what actually gave me the idea of creating a proper render of my PCBs is Altium and its 3D capabilities. So yeah, you press 3 and then you have your 3D model. That's assuming you've actually got the step files for your components. Most engineers or most designers they don't have any step files, so it's just the footprint or just a basic sort of cube, ugly gray rectangle
right,
sometimes.
take some
Uh,
care
so
to put it in the actual models.
yeah, so and unfortunately, most engineers they don't bother much with that. They just ensure they've got the 2D layout done correctly, and They don't put
Yeah.
too much effort into the 3D part of it.
So, would you be able to show a little bit about how this works? Kind of give make it concrete.
Sure. I'm going to just share my screen and just so I'm using Altium's online 3D viewer, and I've got this PCB that I've worked on, and this is a simple 60 watt DC-DC converter. You have your DC coming in here, and your DC out comes in here, 12 volts or 24 volts, I'm not sure. Anyway, it's this is Altium's 3D capability, and well, this is how it looks in 2D first of all, um, and 3D it looks okay. There's nothing wrong with it, but it's too perfect. Certainly the components, the 3D models that I have for my um, capacitors are just cubes, and they're all the color is not correct, and but it's certainly not bad. It does give, it certainly tells you what this circuit looks like, and you're able to make out where how the connections come in and come out, and mounting holes, and then you've got a shield as well, which looks like it's actually the 3D CAD model is very good. You can see that it's even got the shield has these cutouts here and here. So some components are better than others, I would say. But this is absolutely fine. But then it doesn't sort of tell you how. Okay, this is if you want to how the cables come in, for example, your cable management. How does that look like? Yeah, I got two cables coming from here, but then will they sort of interfere with something else, or um, and also like measurement and probing. How can I sort of probe this? And if I had my probe coming in, would it collide with this capacitor, for example? So things like that could sort of be useful it's useful to expand this 3D scene and add more objects and elements to it. So that's sort of how I have this is the design that I have in Altium right now. Um, and so then how do we take this design to Blender? Well, first of all, there's a few steps involved in it. There's no, unfortunately, one button where you press and that takes you to Blender. So there's a few steps that you have to do. So first of all, I start with the Gerbers. So we generate the Gerbers for this board. It's a 6-layer or a 4-layer board um, for this. So we have the Gerbers, and then we need to convert those Gerbers into an image. So to do that, there's a website called Trace Space, which I really like. And what you do is with this website, you just drag and drop your Gerbers into this. Um, and you can it's a good viewer to show your Gerbers and just to
Hmm.
confirm that everything is correct. But what's nice about it is that when you click on this button, you can download. It converts your Gerbers to SVG files, and so once you have your SVG files, you can load that into another software, which is Inkscape. And then from there, you can export the individual layers. Um, so you can export, for example, I can turn off the individual layers, and um, like here, I'm just showing the copper. So I can then separate all the copper from the solder mask from the overlay and export those as separate images, which then we will load into Blender. So
Is
that's
the
that's
format for that? Is that the format for that SVG still, or is it a raster image?
Oh, it's a rastered image, either PNG or JPEG. So unfortunately, Blender it can import SVG files, but the
Hmm.
amount of detail in this PCB will make Blender very slow. So it's certainly one way of doing it. But and the other problem you might have with an SVG file is because then you will have to convert it to a mesh, and the mesh tends to be quite dense. So it's my approach that so far that I've been using is to convert this to a high resolution rastered image, and then you would load that into Blender. So if we go to Blender right now, and I've prepared sort of how the scene. Okay, let's hope. works. Let me sort of just take it back to basics. So let me just hide some of the components I have here, and let's just show what's happening. So this is essentially the PCB, and if we go to this view where we don't see any materials or any shaders, this is basically a cube with the mounting holes on it, and this is the dimensions of it. Now, starting with the PCB shader and how do we load our images into this? So um, I can't go into all the details and how I created
Wow.
the shaders because it takes a long time, but I can sort of very briefly discuss. So I've created this. This is the shader, and I called it PCB top, which means it's only the top layer. And then I could load in all my images. So then I've got the drill file, which I exported from Inkscape. I could then load in the top copper, which is also a PNG file, and I've got solder mask and I've got the overlay. So that's all you need basically. Solder mask, the overlay, solder mask, and your copper and drills. Um, and that's all you need to create how this PCB here. Um, but then also what you could do is you could add some surface imperfections. So you might see here I've got
Mm-hmm.
just some sort of, I don't know what you call this. It could be dust or fingerprints, and this is what then makes the difference between Blender and other and Altium and CAD. Basically, you can add all of these imperfections, and you can see here. This is my sort of my node setup here. I can add noise, uh, bump maps. You could go to town on this, and you
Mm-hmm.
could customize it however you want. Um, so this, and also I could change the color. So this is green. I could make it red, for example. It's a red PCB. So we could do that. Um, so that's how we take the images from Inkscape and put them into Blender. All right, then comes the components. Now, as I mentioned, we saw in
Uh-huh.
the components that we had in Altium, they were sort of too perfect, I would say. It's just simple geometry, rectangles. Some are better than others, like this connector is really good, um, but others are not. So what I've done is in Blender, I've created my own sort of library of components, such as the capacitors, 0603 capacitors, 0402, and other components. And so then what I would do is I would load them into my scene. So I would load them all here on this plane. And then right now it's a manual process where you have to sort of you have to manually add the component, move the components onto the pad. So it's like a pick and place machine, a manual pick and
Right.
place machine, let's say,
I was
at
just
the
thinking
moment.
that. Yeah.
Yeah,
That's
it's a
pretty
manual
funny.
pick and
Kind of a video game version of real life.
yeah. Um, I'm trying to sort of to find a way to automate this, especially if you have the XY data or your pick and place data.
Right. Right.
Um, there has to be a way of then getting this into Blender, and then instead of you having to do it manually. So for example, let's say I've got these are the capacitor 0603 capacitors. So then I would just go into Blender's edit mode, click on the capacitor, and duplicate that and bring it here. And then we need one more here as well. So you can that's how I'm currently doing it. It's a painful process, especially if you have a big PCB. Um, but it can take time. But for these sort of small PCBs, it takes about five minutes or so, maybe 10 minutes to do that. So
And what do
that's
you
how I would
use as the reference for what parts you need? Kind of like the bomb and that kind of thing.
the
And
bomb.
which parts go
Yes,
where?
exactly. So I need to know the bomb because this is my design. So I pretty much know I've got an 0603 capacitor. But if it's a design that I got from the web from somebody else, then I will need to have the bomb. And so to kind of so yeah, I have my bomb on one screen and Blender on this screen, and I have to sort of check. Okay, C17 is this capacitor, C13 is this capacitor. So yeah, it takes a lot of time to do it because it's a manual process. So this is something I'm looking to automate, this process to make it quicker, especially with these passives. For other components like connectors, because there's only one or two on the board, you could place these manually. So for example, this is a connector. You can see I actually took the step file for this and changed it into a mesh, and I just then added some surface imperfections on it on the connector. So this is the, if we go to Blender's um, solid view mode, you can see this is the actual mesh from that I got from. It was initially a step file, and then you convert it into a mesh. Um, and generally, the mesh tends to be, if you convert it to a mesh, the mesh tends to be not very good. So you can see, I mean, here it's not that bad, but sometimes um, you can see right here that the shading fails in this area because the mesh is not done in a good way. So you have to be careful with importing meshes or converting step files to mesh. It's always best to create the components natively in Blender so that you can get the best shading result. So if we just go back and Blender now with the new version of Blender, it has something called a asset browser where you can create 3D models, save them as in your library, and then you could easily load them into the scene. So if we take this connector, for example, I've made many of these connectors. So it's a through-hole connector, and it is this one right here. Just drag and drop. There it is. And sometimes you'll have to do some adjustments to it, alignments, and this needs to rotate like so. Um, that's that. So yeah, and that's how you do it. Um, Same goes for this component here. This is transistor, a power transistor. I've made this before and I've saved it in my assets in Blender, and I just um, drag and drop like that. And some adjustments that need to be done. So it's not bad for kind of these components, but for passives, it certainly takes time to do. And that's how I do my PCBs. Yeah, so it can take about a full day or up to 8 hours sometimes to kind of
Hmm.
have a PCB like that. So this is how I would do it. Um,
Well, it's pretty cool that you can spend 8 hours and come out the other side with a really nice piece
yeah.
of art. Essentially, that's
Exactly. And the nice thing, okay, so this is now the PCB. Okay, well, let's add more items to the scene. So again, I've create this. This is a mat, let's say, or okay, like here, like so. And then let's say we need to add maybe like a cable bundle to the scene. Um, so some cables in there, a probe. We doing some measurements, so we need um, a probe hook in there that we could use. I've got some tweezers. Maybe I need to pick some components. I'll put some tweezers in there, and yeah, you could just and then I've got a IC tape. Okay, so sometimes you've got components inside tape there, and like so. That's how you create a quick scene, and then you can adjust the lighting of this. So this might be a bit too bright. I like things a bit dark, Joe.
yeah.
um, so you could adjust the lighting a little bit, turn off the lights, and then we could add some different kind of lights to the scene to make things Um, so it starts to become real, or it looks almost real very quickly. The moment you add these cables, items in there, it starts to look really, really cool. And so, for example, if we look at another scene that I've prepared, um, a more complicated scene, Okay, let's hope Blender would work for us. There it is. Okay, so this is a more complicated scene where um, I took one of your boards, your that you create, and I just made this scene here where I've got these probe hooks. In the background, I've got a display showing all your measurements that you might have, and it generally it is a kind of a messy scene, but that's how all these electronics benches are. You know, you've got
Tend to be,
cables
yeah.
everywhere, tend to be, yeah. And because of getting really close, and I've even modeled the solder as well, the solder
Mm-hmm.
on for the components, and that's all done using Blender has a new feature called geometry nodes, which allows you to create procedural objects and effects on components. So if you go back to if you go back to this scene here, so if I click on these solder pads, and if I go to Blender's geometry node editor, and if I enable this, and all of a sudden I've got solder pads here, or solder joints on my components, and they sort of vary in in height depending on how big the component is. So for these 12010 caps, you know, they're slightly large, but then for example, for these 0603 capacitors, they're slightly um, smaller, let's say. So um,
And
yeah,
is he able to do that based on the geometry of the pad object?
on the geometry of the pad object, absolutely, yes, yeah. So that's uh, uh, how I do it, yeah. And of course, so here's the node that does this. So this is basically what this is doing is okay. It's saying that there's geometry coming in and geometry coming out, and then we are doing something with this geometry, what this node does. So if I disable this node, then basically all I have is let me just zoom in. Uh, all I have is just these are the paths. They're just
Hmm.
squares, very simple geometry, just four uh, vertices here. But then if we go into this one, so what this one then does, it takes the sort of the XY coordinates, takes the area size, and then extrudes the mesh, and then adds a bit of surface imperfection on it as well. So um, yeah, you could do so much with it with this one. So that's how I create my how I do these renders. Yeah. Also, you would notice on this inductor again surface imperfections. It changes everything. You know, once you it makes it look a bit more real. And
One thing I wanted to ask about this is, do do you carefully look at the part to try to see like how you can change the settings in Blender to make it more real?
I try to do that. If you the more generally the more surface detail you add, the more realistic it looks. But then that takes time and certainly makes the mesh more dense. So you got to sort of make a decision. Okay, how much detail do I need to add? If the camera is pointing far away from your scene, then there's no need to add too much detail. And actually, Blender does not render any sort of fine details. It only sort of uh, 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 it starts to render these details as you get closer to your object, which is really good. Um, but for large for large scenes, then there's really no point in putting too much effort into the fine detail. So for example,
Hmm.
I would maybe not put the solder um, uh, joints if I'm taking a render from this distance, for example. There's no point. It would just slow down Blender. But if I need to get really close, like a close-up image, then you start adding more detail here and remove details from other areas in the scene. Yeah, it's generally quite what Blender does. There's something called in the modifier settings, adding a bevel modifier makes a huge difference. So if we look at this component here, this connector, and let's just zoom in into that a little bit, you can see that the edges, they're a bit they're a bit round. They're not sharp as in the CAD models. So
Mm-hmm.
you can see now this is, if I turn this bevel modifier off, you see it becomes quite a very sharp edge, and that's not really what happens in real life. And then, but then if you add that bevel, it adds, and also the shading and the light also changes,
Mm-hmm.
and that makes it looks more convincing, um, than without that bevel. So it's such a simple thing, but if you look at this screw here, adding that bevel just makes it look a bit more shiny, and
Mm-hmm.
makes it a bit more
Like a real
believable. So
manufactured part.
exactly, yeah, yeah. And this is sometimes you might see that in CAD models, and others you don't. So if we go back to the Altium one, um, again, these resistors, they're just sharp edges. Sometimes this inductor here, it has the bevel on this
Mm-hmm.
edge here, but not here. So yeah, it's these sort of tiny things that, um, Blender really excels at.
So one thing I noticed is you're able to somehow combine your work in electromagnetic simulation with this rendering, so you can put in field lines and that kind of thing around inductors.
Oh yes, yes. Let's for example have a look at this one here. This is one of the first circuits that I built in my research to demonstrate wireless power. So on the left is
Mm.
my transmitter, and on the right here, this board is the receiver. And this is my transmitting coil, and this is the receiving coil. And what's happening is, simple physics, induction. We're passing a high frequency current into the coil, generates a magnetic field, couples into the secondary coil, and then there's a rectifier in there, gives you a DC voltage. So DC comes in the end, DC comes out. Um, so this here is basically two turns of wire,
Mm-hmm.
and is sometimes useful to illustrate what does the magnetic field look like. Um, and uh, and so it's very important to know where the field lines goes, and so then you're able to, because it might interfere with other parts of the circuit, and so you need to be careful with that. And also shielding is important, and safety as well. So you need to know what the magnetic field looks like, for that. Now, there's many ways of doing it. If it's just a if it's just a single turn or two-turn coil, no ferrite in it, you could basically use Physics 101 to work out
Mm-hmm.
what the magnetic field is. Um, and certainly you could use, for example, Biot-Savart's law to give you the magnetic field, for that. But what's more difficult is working out the inductance of this coil, and because then you would need that value to design your amplifier circuit for it. And so, to calculate the inductance, especially if you have a certain type of geometry, or a weird geometry, you need to use certain software to do that. You can't rely on equations anymore. So as an example, one of my papers where, um, quite interesting one, which we just want to demonstrate wireless charging or wireless power for drones. So the idea in this paper is, essentially what we have. You can see this is my early attempt at, doing illustrations and renders.
Right. Right.
Um, so this is again from Altium, and then I just copied this image of the drone. Well, here what we're trying to demonstrate is just a demonstrator, is to make this drone hover over this pad and
Mm-hmm.
be powered completely wirelessly. It has no batteries on it. So all the energy is coming from a magnetic field, the transmitter, couples into the drone, um, and then the drone then gets powered by that. So if I sort of go a bit more detail into the drone and how we did it. So essentially what we need to do is, this is our drone. We need to kind of build a coil around it so that we can capture the magnetic field. the thing with drones is that they can't carry any weight. So if you add a coil to it, that adds weight, and then you need more energy, and then eventually the motors are not powerful enough, and it won't take
Mm-hmm.
off. So what we did here is I took the guard of this drone, a piece of plastic, and what I did is I put copper tape around it. So then that formed a single turn coil, let's say.
Mm-hmm.
So then I needed to work out what is the inductance of this coil. And so that's when then and that's where the challenge is. We need that inductance because then we have to design our circuits for that. So the way I did this is, okay, I again went to my favorite tool, Inkscape, just draw a simple geometry. This is how maybe the coil might look like. Inkscape, okay. And then we save that as an SVG file. We go then into um, FreeCAD. FreeCAD is another great piece of software, also free. And FreeCAD has the electromagnetic workbench, which is installed as an add-on. And this
Really?
workbench is, yes, the
That's
EM
great.
workbench. Um, Basically, this uses solvers from fast field solvers mainly. Another piece of free software. The thing, Joe, with all of these sort of free software is that there's no one that does all. You kind of have to move from one tool to another to do your job, and that might be confusing for many people. So there's many pieces of software you have to go through to get to the result that you want. So we start from Inkscape. We went into FreeCAD, and we're using the EM workbench, which is based on Fast Field Solver, which you have to install separately. It's a separate installation.
Mm-hmm.
And then you basically generate. So what this workbench does, it creates the script for you that you would load into Fast Henry or Fast Field Solvers. So this is the coil that we designed. I can specify in for the solver, I can specify the frequency range that I'm interested in. So I'm interested in between 100 and 35 kilohertz up to 13.56 megahertz. So I want to know what is the inductance over that frequency range. Um, so then, what this software does, then it generates what this tool bench does. It generates the script for you to then load into Fast Henry. So then when you
Does that
open Fast,
script primarily create the geometry within that environment?
yes, yeah, exactly, creates the geometry. So then this is how the code then comes out from that workbench, and this is what you need to load into Fast Field Solvers. Um, and so, as you can see, it's if you want to type this manually, it's pretty much impossible. So you
Right.
need a tool to create this script for you. Basically, what this is telling you is that this is the XY coordinates basically of your mesh. That's what is it doing basically, and it
Of something
specifies other
that's
parameter.
a copper type object.
Exactly, yeah, yeah. So then what we do, okay, so this is, and of course it has its own 3D viewer, and this is, okay, this is our
Mm-hmm.
coil. Okay, so I want to know what the inductance of this coil is. So I've got my script now, and I could sort of run the tool, and it doesn't take that long actually. So now it's running, and you can see here it's trying to solve, just doing some stuff, some math, and
Mm-hmm.
there we
Some
go.
math.
Um, so now it gives you this matrix of your resistance and the
Mm-hmm.
impedance or the inductance. And this is what we were interested in, the inductance and also the resistance
Across
as
multiple
well,
frequency points.
across multiple frequency points. So we started with this frequency and we ended up at 13.56 megahertz. And this is the inductance that we have. So the inductance is 600 and almost about 670 nano henries, and the resistance is 0.17. The interesting thing is that as you go up in frequency, the resistance of the coil goes up. So at lower frequencies, it's only 40 milliohms, but then as you go
Mm.
to so at the kilohertz range is 40 milliohms, and then you go into the megahertz range, you're almost 0.175 ohms.
It's like a ferrite
So
property. Is that right? Like the idea that it becomes resistive.
it's because of the something called the skin effect. So here,
Hmm.
this is just an air
Less
core.
of the
Yeah, so as you go up in frequency, the current starts to force itself towards the surface, close to the surface or the edges of the copper. And so there's less surface area or less cross-sectional area for the current to
right
flow,
for the current.
and
Yeah.
therefore the resistance goes up. And that's generally not a good thing. It's one of the very challenging thing. One of the issues you have when you go to megahertz frequencies is that your coils become lossier,
And
tend
what
to become
happens as
lossier.
that frequency continues to increase? Does that just get worse and worse till you're at sort of like a single layer of electrons that are
Yeah, it gets worse and worse until the resistance dominates. So the resistance becomes more higher than the inductance or the impedance. But
right?
then you start to get into other effects. So here, what this tool, it only calculates the inductance. However, at megahertz frequencies, you need to be aware of the capacitance as well.
Mm-hmm.
So, but for now, we're going to keep it simple because we have just a single turn coil. So if you have multiple turns, then you need to start to think about the capacitance between those turns as well.
Mm.
So um, and that then starts to have an effect, and then you have a resonant frequency of the coil. So it starts to be it starts an inductor and then ends up as a capacitor as you go up in frequency.
And you want to basically, what's the optimal point to operate it at then?
Well, the optimal point, that's a very good question. There's something called the Q factor. So as a good
Mm-hmm.
example is uh, some of the data sheets of inductors, they give you the Q factor curve. In fact, if I pull up a quick data sheet from Coilcraft, um, so if you look at, for example, this is a coreless inductor, air core, and so they give you these curves. So they give you the inductance curve um, and over frequency, and then they give you the Q factor curve. The Q factor tells you, okay, you want to operate. It's the ratio between the reactance and the resistance. You want to operate your inductor at its maximum Q point, and that's where you get sort of the ratio between energy stored and energy dissipated is the
Mm.
highest. Um, and so you want to operate at, so as you go up in frequency, although it might seem the resistance is increasing, but the impedance also goes up with frequency, so that helps you. But then as you go up more in frequency, then you start to reach the self-resonant frequency of the coil, and then the Q factor drops, and then becomes a very lossy component. Um,
Because it's
so
so resistive, but at the same time not very inductive, or
not very inductive. Yeah. So it becomes and then starts to radiate as well. If you approach the lambda, the quarter wavelength of the coil, it starts to radiate. So you really want to for this so for if you go back to our paper for this type of geometry of coil, you don't want to be going too high up in frequency, otherwise it becomes lossy and it starts to radiate. Then you have issues with EMI as well. And you don't want to go too low in frequency because your Q factor is going to be very low and therefore your energy transfer efficiency is low. So you want to sort of operate in somewhere in this region. And that's why I'm working at, for this project, I was working at 13.56 megahertz. So
Mhm.
in this region here, basically. That's where I was working at. And so that's the answer to your, so that's a long answer to your question. Yeah, you want to really operate your coil, or you want to design your coil to have a very high Q, the highest Q at or close to the frequency that you want to work at.
I noticed in that simulation you just did, it didn't seem like there was any wires hooked up, so to speak, to the coil. Like it was just sitting there in free space, and then
Okay.
from that itself, you were able to compute what inductance means.
Yes.
Uh,
So one thing I didn't talk about, Joe, is if you go back to our first drawing in Inkscape, see here I haven't joined these
right.
two wires, and that's because this is where then I tell uh, fast field solvers that the current I want to measure the inductance
Okay.
between these two terminals here and here. Um, those will be my
Okay.
terminals,
So it's
and
part of the settings in that
it's
in the
part of the
FreeCAD here.
settings. Yeah, exactly. And
Okay.
you see
Oh, I
now
see it right there.
it gave me this arrow, or I told FreeCAD that this is where the port is, let's say, here,
I see. Okay.
for that. And so then when you calculate the inductance, this is the inductance value looking into that port. If you then start to add wires here, of course these will
Mm-hmm.
impact your inductance, and it's always best to actually model those wires as well, that so that then because they will impact your circuit. So if you go back to the paper, you can maybe it's not shown, but see I've got maybe two wires here, and it'd be useful to actually they're just right. Maybe you can't see them. We're just right here. Um,
Mm-hmm.
it's good to have these included. They, they can be quite complex, so you know it depends. If they're quite long cables, then it's best to add them. Otherwise, if they're too complex and they twist, then that might make the mesh more dense and take more time to solve.
Mm-hmm.
Um, for that. So okay, we've worked out what's our inductance, and then we can then design our circuits. So this is the amplifier board. And then we can then choose the values of the components that would work with this coil that we have. And so then I would what I would do is I would then go to Spice, and I use Symmetrics as my favorite Spice simulation tool. It's just a better user interface, I think. And so we got the inductance of about 670. So and then it's going to be this component here, 670. So what this circuit is, this was my transmitter. DC comes in and drives the transmitting coil by current. And this is the coil that we just simulated right now in Fast Henry, that on the drone. And then this then will induce an AC voltage with then, and this is a rectifier and gives me a DC voltage out, which then that would go into and power the motors of the drone. And then I would just put that in Spice, um, run the simulation, and we should start to see some waveforms and some waveforms here. And this tells me that this is my DC voltage coming
Mm-hmm.
out from the drone, just under 12 volts for that. So this is my DC voltage, and and then on the top are the waveforms of the inverter, of the amplifier. It has this sort of waveform, and this is the waveform of the rectifier. So there's a lot more detail into this, but I thought you know the key thing here was, okay, how do we work out the inductances? Because then that
Mm-hmm.
basically impacts everything else in the circuit
And
for it.
considering that you optimize for a very specific frequency, you'd want to have
Yeah,
the minimal harmonic content then in that part. So that seems
absolutely.
like a really key part of the
It
optimization.
is. It is exactly. That's a very good point, Joe. Yes, because then you have to design all your filters and everything, the right impedances to work with that coil.
Because
Yes. So
I imagine the switcher is very high harmonic, sort of obviously, right? It's a
yes. Okay.
on off.
Yeah. So with the switcher or the inverter here, and that's the other sort of the other contribution that I had from my PhD in research is, as I mentioned at the beginning, Joe, that I developed some new circuit topologies in power
Mm.
electronics to work at these high frequencies very efficiently. And this is how the actual amplifier circuit looks like. It's a new type of topology called Class EF inverter. There's Class A, Class B, Class C, and you might have heard of those amplifiers.
Mm-hmm.
This is a switch mode type inverter. So theoretically, because of switch mode, the efficiency should be 100%. But
Mm-hmm.
in practice, it's not. You have some losses, and it's all about getting zero voltage switching on your waveform. So if you look at the experimental results here, what this is showing is VDS, the voltage across the transistor. So when the transistor is off, it has this sort of it's not a square wave, unlike your PWM converter or any kind of converter, but it has some kind of harmonics in it. And then the moment you switch on, it goes to zero, and that so um, you have zero voltage switching, and so then you're able to work at these. megahertz frequencies and still have a high efficiency because of that 0 volt of switching. The challenge though is that the other challenge is that that 0 volt of switching only happens for a fixed load. And so many of the circuits before, they were also using class E type variants where you would only have 0 volt switching at a fixed load. So once your load RL here changes, and in this case, the drone hovers around, so that load will keep on changing, you lose 0 volt switching. Uh, what my contribution was is that I was able to keep the circuit in tune inherently, while as the load changes, I always get 0 volt switching. So let's go back to our waveforms here. And so yeah, here I've got multiple waveforms stacked on top of each other. And you can see this is sort of all the power levels. And you can see that I'm always maintaining almost perfect 0 volt switching, almost, some variations, as the power changes. So that's been the other contribution that I had for my PhD. And this is I had to get rid of the saturable reactor here. It wasn't efficient enough. So yeah, this is
That's super
sort of a quick
cool.
summary of.
Anytime you have a new amplifier designation,
Yeah.
that's pretty big deal.
And the other thing that helps a lot is the transistor, the semiconductors. So what we're using here is a GAN transistor. So it's not a silicon transistor, it's a GAN, gallium nitride transistors. You might have heard um, the term wide bandgap semiconductors, and this is what they allow you to have faster switching speeds, and they require less energy to turn them on and turn them off. So then you can work at very high frequencies with them. But they're quite fragile and delicate devices. So this is it's the GAN transistor that we are using here for this.
Fragile in terms of the electrical current feeding required, or in terms of
Yes,
mechanical.
both I would say. So they're very small devices. In fact, let's go have a look at one of them. So one of GAN systems is one example, or maybe EPC is another one where they have even smaller devices. So let's look at EPC. And let's take an example. For example, let's have a look at this one. So this is how the size of this transistor is only 6 milliamps by 2.3, but you see the ratings on this one. 590 amps, 30 volts, and it's in this type of arrangement. So usually with a silicon transistor, it would be in a large TO220 or TO247 package for these type of currents. But this is such a tiny device. It's fragile. It's um, in terms of volt. So yet the gate drive, you've got quite a small narrow margin to work with. If you exceed that margin, you would fail. Um, how do you then extract the temperature? Thermal becomes the challenge. Thermals becomes a very big challenge because it's such a small area, and so how do you get the heat out of it? Can be quite difficult. So this is EPC. GAN systems generally have slightly bigger packages to work with, and easier sort of. They help a little bit. So um, this is one of the transistors that I was using. 650 volt type, and you can see here it's got a big thermal pad on it here. These two pins are the gate drives. So this one is a bit more easier to work with, but still it's a hot spot in your circuit. And as long as you're able to extract the heat properly, you certainly can get them to work very, very well, and certainly make the entire system more efficient and better. However, having said that, they are a bit expensive, a bit pricey compared to silicon. The price has been going down but it's still slightly higher than silicon.
So a part like this, what kind of price range is it in?
So with this one, if we this specific one is, I think, expensive. If you go have a look at Octopart, and let's just see what Octopart tells us. So my currency is in USD. So you can see it's quite expensive. We're talking
Hmm.
$15 for 10,000, $14 for 10,000. So certainly a pricey transistor for it's not that cheap. Whereas with silicon, maybe for the same ratings, it would be like $1, for example. But then it
Hmm.
can't work at these high frequencies. That's the thing. So
Oh,
you're
okay.
pretty much limited in choice. Um, so the key thing that enabled this piece of work on my research in general was two things. First of all, the circuit topology and the availability of these semiconductors. Without those two things, this will not be possible, or it just would be very, very inefficient for it to work.
What part of the inefficiency is in the sort of coupling? I guess how do you think about the inefficiency of the fact that you're not running a wire versus the inefficiency
Yeah.
in the actual power converters?
Yeah. So of course, having a wire directly from your from the source to the load is just going to be the best way of getting power across. It's going to be very efficient. But in this application is where you can't use a wire. There's no way of putting a wire in there. And so you have to use some form of inductive coupling. And so the losses mainly come, so the uh, the design of the coils, you have some control over that. So as we mentioned about the Q factor, so you can get that Q factor very high. And so you can get like a coil to coil efficiency of about 95% or something like that, in
Hmm.
that range. So it's quite high efficiency, but then the losses occur in the power electronics generally. And so if you're using a Class A amplifier or Class AB amplifier, it has a theoretical efficiency maybe up to 70%, 60%. So you're pretty much losing most of your energy in the electronics. And so um, if we can get the efficiency of the electronics to be above 90%, then overall our system efficiency, if you multiply, say, 95 by 95 by 95 by some other more, if you have more stages of
Hmm.
conversion, you end up with an efficiency figure between 60 and 17, worst cases, maybe best cases 75% efficiency um, for the entire system. So, and of course, so which means then that means this sort of tech for a consumer product, it's not going to be, it's not tailored for consumer products because of the efficiency is still going to be low, and then you basically pay for that efficiency. It's only for applications in sort of defense and industrial applications where it enables new features and they're willing to
Hmm.
accept a lower efficiency to get features that you want.
So,
We want.
so
So
in my intuition on this is that you put those coils right next to each other, they're very tightly coupled, and
yes,
as they move farther apart, and let's say there's in the middle of nothing, there's
yeah.
no other objects around, right? What does that coupling, is that impacted in any way? All other things being
It
equal
is.
as you
In
move it
fact,
apart.
Joe, in fact, if I show the next generation of that work, where we actually took a proper, this was my research group back in Imperial College, um, and what we did here is then um, we took a DJI drone, the Matrice
Hmm.
100, and then we actually demonstrated this uh, how this would work. So if I zoom in here, expand this. So what you see, here's the big drone, and you see
Hmm.
this loop
Yeah.
here. That's our coil. And again, because if we work at a very high frequency, we can use a single turn coil, and it's very lightweight. And so the idea is that this drone would land anywhere, would land on this platform anywhere on the
Hmm.
platform and charge wirelessly, completely wirelessly. So we're transferring energy from this. There's our transmitting coil is under this white pad here, and that couples energy into this coil here on the drone. And so the drone could land anywhere on the surface. And of course,
Hmm.
the further away from the center of the surface, the lower the coupling efficiency. So of course, we design for the worst case. So we assume if the coil is all the way towards the edge, we know the efficiency is going to be about, say, 80% or 85%, the coil to coil efficiency. So that's going to be, that's what we design for.
What
But we
happens
always,
to the what happens to the the energy that's not being transmitted?
Heat just goes into heat.
Into the air
Uh,
though, or where?
no, it's because of the coil to coil efficiency has dropped, we have to pump more current into the coils to get the same magnetic field.
Okay,
So,
so it's more lossy because of the resistance in the coils.
yeah, because we're driving higher currents into the coils, and so
Okay,
higher current means I squared R losses goes up
right.
quite dramatically.
Okay, so there's no actual
Uh,
fundamental. It's not like you're losing radiating energy
oh
into the
no,
universe or anything like this. It's
absolutely not.
only
No.
going to the other coil, assuming
Yeah,
everything's tuned.
exactly. It's only most of it is heat. There's no energy radiated, or there's no other objects in the area where energy gets coupled into it. So if you have metal, for example, then you would
Hmm.
couple energy into that. So
And
um,
that causes electrons to move back and forth and burn up some
yeah, you would
resistance,
induce eddy
or
currents into those objects, and so
and basically heat
that's
them up.
why heat them up, and that's why again this sort of tech is not suitable for consumer uh, products because they could be any kind of sort of objects, in the
Right, and
environment.
100 watts would
Exactly.
be
We
interesting. Yeah.
did go to higher power levels, 700 watts, charging of e-scooters and stuff. So we did go to much higher power levels, and so there's more videos on this webpage. We're
Yeah, this is
also on
a
the news as well. But what we tried to do, drone drone to sensor or drone to drone wireless charging. So you've got mid-air refueling of
yeah.
jet fighters.
That's like super sci-fi right there.
Yeah. So this was an interesting experiment where um, if the video is playing, I think it's okay. So what we did here, instead of transferring energy from the ground to the drone, can we transfer energy from the drone to other areas? So here what this is
Hmm.
showing is a drone to sensor. So you have these sensors maybe in certain environments, certain areas where they're buried
Yep.
underground, hard to reach to. So the idea is then you would send a drone over and they would just charge these sensors.
I like that. Yeah, like yep. Where there's no solar, I suppose, that where you need to do that.
Yeah, exactly. Or if it's hidden underground or it's
Hmm.
just, shade. The video is not playing, but still buffering. Okay, there we go. We also had this drone flying next to it to film it and also to see how close can we get to the coil here. What's
Hmm.
not shown in this video, eventually this drone crashed into that one and it just vaporized because it's such a big drone. It just tells you that for this sort of thing to work, drone to drone charging, it has to be fully automated. Having
Hmm.
someone a pilot to manually pilot this thing is impossible to make it work. But the video is not playing for its buffering, but I can send you a link to it and you can see it in more detail.
This is a
But that was
fascinating
quite a fun
area.
project. Yeah.
I don't know. This makes me think of actually is put a can you make it use an electromagnet to induce a force in another drone? Anyway, it's
Yeah.
just lots very interesting
It's yeah.
kind of
So
area.
so the other sort of applications for these high frequency wireless power or high frequency magnetic fields is in plasma generation. So they use them in plasma thrusters and
Hmm.
in space to especially in satellites to maintain orbit. Um, so they use these plasma thrusters. Yeah, I have to, and that's the other area where you could use these high frequency circuits. Because again, in space, it's all about efficiency. You want less energy. You want no heat to be generated. So that's another area for these circuits and for these semiconductor devices as well. So that was sort of my research, Joe, and so that's the nice thing about academia sometimes is that you could experiment and play with all of these ideas and concepts, and as long as you have the resources, of course. Um, and so yeah, that was my research.
It was fascinating. Uh, uh, I mean, I kind of ran out of time. Are you doing okay? Keep it 5 more minutes, or
Yeah, I can carry on. That's absolutely fine. Yeah,
okay, great. Maybe five more minutes or so. Let's see.
no worries. Yeah.
Um, I wanted to ask you about your favorite electrical engineering book and
Yes.
kind of why it's important to you and why you would recommend it if you do.
So my favorite book was a book called Practical Electronics for Inventors by Paul Scherz, I believe his last name. What's nice about this book is that it sort of it didn't have too much mathematical detail. It covered broadly all the different aspects of electronics, starting from the basics, components, resistors, capacitors, transistors, and how all these circuits work in such a very clear way. So I would highly recommend this book for someone who very early in their career stage or in education. And it's a good way to get into electronics without having to deal with all the complicated math and physics
Mm-hmm.
that are associated with it. So that's been my favorite book, and I started to use that book when I was perhaps 14 years old or 15. I'm now 35, but I started using it when I was 14 years old, and that's how it got me into electronics. That book.
Was there someone in your life that introduced you to that book, or is that something you found on the library shelf, so to speak?
Um, how I got into that book, and it's I had I had an interest in electronics at that time, so I was one of those kids who would break their toys to see how they work. Really gave my parents a difficult time because they would buy me a new car, remote controlled. Okay, it works. Okay,
Mm-hmm.
let's break it and see how it works. So I had this in my bedroom. I had a bench where I had a collection of motors, wires, lights, and batteries, and just hook them up together and see if something could work. And that's how I was interested in electronics. Um, of course, we had the internet at that time, but I think I felt having a good book that sort of had reliable information and an easy way to explain to you for once you get into integrated circuits and transistors and how they work. A good book certainly would be. And so I just searched online at that time, and
Mm-hmm.
that came up as my first choice. Okay, so let's try it, and that's been the book I use. So
Fantastic.
that's the book, and then once I got into university, then yeah, my other favorite book is physics. Um, by I forgot the title, Joe. What was the title? Uh,
Physics for
Physics
scientists and engineers,
for
is that right?
scientists, and yeah. So my other favorite book is Physics for Scientists and Engineers, and that's when then you apply the theory to what you learned in practice. So that book by Paul is sort of more practical, less theory, and then when you learn physics, then you apply that theory to what you've learned, practical experience.
I
Yeah,
see.
so that's my other favorite book.
Fantastic. What what advice would you share with your younger self?
Yeah. So my the advice I was saying is that three things is learn as much as you can. Try to take advantage of the resources and tools that you have, especially if you're in university. There's a lot of resources available to you, but I think most students they don't take advantage of that. So you get access to you have free access to publications, journal papers. So try to take advantage, try to learn as much as you can. And also learn software tools. There's no need to master everything, but as long as you get exposure and be aware of what software can do, what the limitations are and what other avenues are available to improve on. As long as you're aware of all these things, that will really help you going forward, I think. So learn as much as you can, I would say.
Mm-hmm.
Yeah. The other thing is again going back to improving your presentation skills. Have being able to it's one thing being able to do really good work and to create and invent new things, but if you can't present it very well, that's it's hard then to take it to the next level and then build on that. So I would say certainly improving your presentation skills, um, is something is very, very important that will help you a lot in the future. There's that.
How would you go
The
about
other
doing that?
for presentation is
Yeah.
don't dwell too much on the theoretical details. Again, don't put too much text. Don't focus too much on theory. Try to see the big picture, and then explain how then sort of your work can actually is used, and how it integrates with with other parts of the system, or with society, with anything. So try to focus on the big picture and don't dwell too much on the details. If you really want to talk about the details, then you could have a backup slide, for example, or in your report, like an appendix that you could refer to. Okay, if you need more detail, I'm happy to discuss with you, and then you can refer to there. But yeah, try not to, because then it gets boring. If you just focus on the theory or to something minor, it just the entire audience will just lose interest immediately in it. So the key
Yeah, it's
thing is to keep them
quite
interested.
interesting.
Yeah,
I find it for myself, like when I'm working on something, I have this bias
yeah,
that, so I know all the detail and what's wrong with
yes,
it
yeah,
and
yeah,
how it could
yeah,
be
yeah.
argued against, but the person who's like looking at it from the outside is, you know,
Exactly. They have no clue.
yeah, yeah.
Yeah,
And so, like you said, put it in the appendix, and if they ask you a really hard question, you'll have the answer, you know. But
exactly. Yeah. And
yeah,
so visuals is important. That's when we talked about the renders and illustrations and having a nice picture. A picture is worth 1,000 words. A video is maybe worth 1,000 pictures. I don't know. But having a nice illustration certainly helps a lot. And that's just one more thing to add is that also is useful when you go for job interviews. I've noticed that when we used to meet in person, or I would, for an interview, I would actually take physical hardware with me and put it on the table and show, look, this is what I built, and this is how it works. And because
hmm
once you have something tangible in there, you can see it. That really changes everything for that. Nowadays,
absolutely.
with sort of remote interviews and video conferences, you might have to be more innovative. So yeah, having a website or having um, a video on YouTube or something to show what you've done is another way of doing it. Yeah.
Yeah. You said there was a third item as well?
Yeah. So it was the job interview. That was
Yeah,
the third one.
yeah.
Yeah.
I think
Yeah.
that is particularly
Yeah.
correct in my experience. Is
Yeah.
showing something physical, anything at all that you can show that
Exactly.
just
Yeah. Yeah.
demonstrates what you have done before.
Yeah.
Just
A
take.
funny story I remember in my current job at Dyson is that when I first went to the interview, the interviewers they brought hardware with them because they wanted to test my knowledge. They wanted to ask me questions. Okay, what does this component do? What does this do? So they brought hardware with them, and then I took my hardware out. Okay, so it was basically like a chess game. Okay, this is my circuit, this is your circuit, and we started sort of to talk about it. Changes also because they are the interviews they have a certain plan, and then when you bring out your stuff, it affects their plan,
hmm
derails their plan, and then you have the
It does,
advantage,
yes.
and you can sort of control the interview a little bit. Yeah,
Yeah, that's funny because that's happened to us as well when we interview
yeah,
somebody coming in,
yeah,
that they bring in something cool, and
yeah,
now we're going to talk about that. So,
yeah, exactly. Yeah,
uh,
yeah.
all right, Sam. Hey, well, this has been wonderful. I very much appreciate your time, and I hope you get an opportunity to meet again. I'll put all the different links to your papers and some of the software you showed and all your awesome artwork. I'll put that in the I guess it's the description below the video. And
Yes.
yeah, I hope people really enjoy it.
Thank you very
So thanks
much,
again,
Joe.
Sam.
Really enjoyed talking to you, and I hope to see you soon.
Yep.
Thanks a
All right.
lot.